Hey everyone, it's Actuary Dude over here, looking at another exam question. So a computer manufacturer is to develop a new chip to be produced from the 1st of January 2008 until the 31st of December 2020. Development begins on the 1st of January 2006. The cost of development comprises of 9 million payable on the 1st of Jan 2006, 12 million payable continuously during 2007. From the 1st of January 2008, the chip will be ready for production, and it is assumed that income will be received half yearly, in arrear, so at the end of the year, or at the end of each period, 5 million per annum. So calculate the discounted payback period at an effective rate of interest of 9% per annum. Okay, so first things first, so if we're just looking at 1st of Jan 06, and so we're starting with minus £9 million we're out. Then we've got some other amount. So during 2007, I'll just put down 2007. We've got down that we're losing. We've got to pay another 12 mil, and we're just doing it over 1 year. It's a continuous annuity like that. So this is so far how our equation is looking. And then at the start of 2008, we're going to be earning some money. So that's going to be going up. And this is the start of the second year. So the whole thing is over here from 2008 to 2020. That takes 13 years that we're going to be getting some money. But the entire project from when we first pay out 9 million, it's going to be 15 years. So over here, how much are we getting? We're getting 5 million per annum. In fact, so we're going to have to discount it back to get the present value 2 years. So times V squared. Sorry, and this one's actually times V, because this is 2007, we need to bring it back to the start of 06. So we're discounting it back 1 year. This one we're discounting back 2 years. And then we're multiplying it by some annuity that's payable. We don't know how many periods it's going to go on for, because we're just trying to find out when we cover the cost of this, I guess in a discounted way. And it's payable every half year, and yeah, that's how it's going to be looking. So this amount over here has got to then be equal to 0, or at least as close to 0 as we can get it. It can't be a negative amount. We've got to cover these costs, so 0 or more. Okay, so now all we're really going to do is just go on Excel and do some calculations. So over here, I'll just start with saying what's I. I'll do 1 plus I, V. We'll find out what I to the 2 is, and delta, just for now. So we've got 0.09, we got 1 plus I, is that bit there. I'll just bring this here. V is equal to 1 divided by 1 plus I2, so that bit over there is just equal to 1 plus I to the power of 1 over 2, or a half, and then that's minus 1 all times 2. So in fact, I'll just put that inside of brackets again and say that's 2 times all of that. So that's I2, and delta is equal to the natural log of 1 plus I, that bit there. So to start with what we've got, and in fact we've got an n somewhere that we don't know what it is, so that's something. Now, the first bit is we're going to start with minus 9 million. That's at the start of our period. Then we've got over here minus 12 million multiplied by a continuous annuity discounted back 1 year, so we'll just multiply it by V, discounting back 1 year, times the annuity itself, which is 1 minus V to the n, and in this case n is 1 year, so to the power of 1, we don't need to do that, divided by delta. And this is how much, I guess, the present value of that 12 million that we're paying in the second year of the whole thing. And then lastly, we're going to be earning some money over here. So this amount here is this bit over here. So we're getting 5 million a year. It's payable half yearly. We are discounting it back 2 years over here. In fact, I'll put that in brackets. So we're going back to the start of 2006 instead of 2008 when the payments begin. And then we're going to multiply it by our annuity over here, which is 1 minus V to the n, which we don't know what that is, so that bit there, divided by I2. And this bit over here gives us something, and then we can add up all our values here, and it's just got to be something above 0. So, for example, if we only got paid for 1 year, we'd still be in debt. So if we just guess some years, 5, we're still in debt. 8, we've paid out, so let's go 6 years. And this is just something you'd be doing on the calculator, just trying in the numbers. You can definitely work backwards and figure it out. It's not too difficult. So over here, it seems to be somewhere between 6 and 7. Now, because it's paid half yearly, it could actually be paid in the 6.5 year. So if we did that, 6.5, that does go in the positive over here, because this is our net present value, this bit here. So at 6 years, we still are in the negative. We haven't yet met our discounted payback period. But after 6.5 years, we will have started making some profit overall. So it's 6.5 years from the start of 2008, because this is just this that's being affected over here, just the positive cash flows that's coming in. So in fact, there's still those 2 years that that haven't been. In other words, there's the 2 years that we have to add on to this. This is just 6.5 years of positive inflow. We've also got to add on the 2.5 years, which means in the end our discounted payback period, so DPP, is equal to 6.5 plus 2, which is 8.5 years. And even though it could be something like 8.2 something something something, it doesn't matter, because you're not going to get your payment until the exact half year occurs. So it's not as if this is being paid continuously, it's being paid half yearly, or we're receiving the money half yearly. So that's the answer to part I, and that was fairly straightforward. I guess if you're quick enough with a calculator, it should be okay. Now, without doing any further calculations, explain whether the discounted payback period will be greater than, less than, or equal to that given in part I if the effective interest rate was substantially greater than 9% per annum. So I guess this just comes down to a bit of logic. If you understand that, let's say, the interest rate and let's just say value, or actually I'll do net present value, there is an inverse relationship there. So in other words, if the interest rate was 1,000,000%, then you'd only need to save $1 into the bank account, which would mean that you would only really have $1 over here, which would then make there would take a lot longer. The discounted payback period would be a lot longer, because if this value goes down, then the negative will stick around a lot longer. So basically, higher interest rates means lower positive value. Lower interest rates means higher positive present value. So in this case, the DPP would increase if interest rates went up. The effective interest rate was substantially greater. And just for the fun of it, let's check it out what would happen in here if I decided to make I equal to, let's just say, 20%. 0.2, look at that, we still owe a whole lot of money. We haven't yet, or don't owe money, we're still in the negative. You know, if it became 100% interest rate, we'd be owing a whole lot. Whereas if we go the other way and it was 2%, we would have covered that easily. So I guess that's just really to prove it right there. Anyway, thanks for watching, and catch you very soon.